Hi, Shmuel. This is the slide that I have prepared to the Congress, for the Congress. I will start presenting myself and you and Xavier Binefa and the different universities. Well, I will start as I was presenting. Hi, my name is Mara Vivet, and I'm going to present our work, which is called Real-Time StereoMosaicing Using Feature Tracking. The authors are me, Shmuel Pelek, and Xavier Binefa. First of all, I will explain the main idea of what we do. We want to generate a stereo mosaic, a mosaic which have at least two different views in order to see it in 3D. For example, if you have stereo glasses, but only using a single camera. When the light passes across the lens in a camera, it arrives from different directions, but these directions are projected in concrete regions in the CCD. If we have a video sequence of a camera moving parallel to the scene, we can use the regions belonging to a concrete region in the CCD in order to create a synthetic frame corresponding to a view, a concrete point of view. If we do this thing in two different regions corresponding to the left and right eye, we can get an StereoMosaicing. When we have a video sequence of a camera moving parallel to the scene, if we align this set in a space-time volume, if we make a slide in the y time axis, x time plane, sorry, we get the mosaic image. And if we do the same in the y time plane, we get what we call we got the epilines, as you can see here. If the camera has a constant velocity and do not have any kind of other movements, vertical and also no rotations, these lines are completely straight. Otherwise, as you can see here, the mosaics that are generated has a lot of distortions, and as you can see, you get a very bad results. So our goal and what we want to do is to make these lines straight. Imagine the hypothetical case, the ideal case, where we don't have no forward motion, no change in internal parameters, no rotation, no vertical displacements, and the camera has a constant velocity. Then, if we track some part of the scene, depending on its depth, we get different straight lines with different slopes depending on the depth of the object that we are tracking. In this case, we can easily model these lines using the equation of a line, as you can see here. In the case that the camera do not have a constant velocity, if we track the same object, we see that the line is not straight, and the way that and there is a problem, because if the line is not straight, the final mosaic will have distortions. So our goal is to make this line straight. if we take the frame and we shift it, maybe the red line will become straight, but then the blue line will be distorted. So the only way to do so is to warp the time. Then in this case the motion model has changed, and now we add the delta t representing the increment of time respect to the previous frame. If we remove two more constraints, the rotations and the vertical displacement, then we get a more complex motion model, which is described as here, adding rotations and vertical displacement. So what we have to find is which increment, which delta alpha, delta time and delta y we have for each frame. And in order to do so, what we have to do is to find a lot of epilines. In order to find these epilines, the slope of each break, what we do is use kernel tracking. Kernel tracking works by placing a kernel on a region, a concrete region, the region that we want to track, and then generate a weighted histogram of this region. We do the same in the next frame, in the frame that we want to see, which is the new location, and we minimize the SSD distance between these two functions. In order to do so, what we do is an approximation by Taylor series, and we make the derivative of the kernel respect to the x and y. Then we will find which is the increment of x and y in the new frame. We use this information, a single kernel tracking, in order to find the slope of each epiline. So we will track different epilines in order to have a lot of epilines to estimate the global motion. So in the case that we have a lot of epilines, instead of having a single kernel, what we do is concatenate all these kernels in a single histogram, and we do the same in the frame that we want to track. In this case, what we minimize is the SS error of all the histograms together, stacked together. In this case, we do not derive the kernel in the x and y. Instead of this, we derive the kernel using the time, the y, and the angle, which is the thing that changes between two consecutive frames when they are aligned in a space-time volume. In order to make this derivative, we use a slope m founded in the previous step, and also using the chain rule, we can make the derivative respect to the time, and also we do the same respect to the angle. And with a single step and computing the pseudo-inverse, we get all the parameters that are needed in order to align the frame in the space-time volume. Here you can see how this tracking works. In here, green circles, each circle represents a kernel that is being tracked, and the colors goes from green to red and represents the error. White circles are kernels created, new kernels created. Pink circles are placed in a flat region that they do not give us information, and black ones are those placed outside or with discarded because they has a lot of error. In here, Shmuel, I will put some information. I will put this information in here, brighted. Okay. Then, after we have aligned all the mosaic in a space-time volume, what we have to do is to generate the mosaic image. To do so, what we do is cut the time-space volume, and then depending on its time in the space-time volume, we select different regions from each frame, and then these regions are projected to the mosaic image, resulting on the final mosaic image. But this has a problem. If we copy directly regions from, if we copy together regions from different frames, because there exists parallax, it becomes in misalignment, as you can see here. In here you can see perfectly where the frames ends and where the frames start. So what we need to do is to try to blend the regions in order to have a better results. What we want to use is multiband blending. Multiband blending works by having two input image and one mask, and then discomposing the image in different frequencies. The blend is applied in those different frequencies, getting a very good results because in high frequencies the blending is not applied. But as you can see here, in order to generate a Gaussian pyramid, you need a big image, and when you generate mosaics with very short strips, it's very difficult to apply this technique. So what we propose is to a new blending, which is called the barcode blending. In this case, what we do is to select twice as the size that we used to use when we generate a simple copy mosaic, and instead of generating one single mosaic, we will generate two mosaics, one for the odd frames, another for the even frames. And in the same time, we will generate a mask which will be used in order to fuse these two mosaics. In this case, we start by selecting the F1, which is odd, so we will copy all the region onto the odd frames, and then we will make a mask starting for black and then white. Then the next frame is even, so we will copy the twice region as needed, and in this case we will make a mask corresponding to each region, starting by black and then white, and so on. After this, if you had these results in the previous approach, applying the barcode blending, you can blend the parts that the mosaic is stitched without losing detail, because the high frequencies do not suffer blending. This is how it looks in a real example. As you can see, it's called barcode blending because the mask, the resulting mask is like a barcode. And this is the result without barcode blending. And applying the barcode blending, look at here in the bridge. If you apply the barcode blending, you see that the results are much better without losing detail. Here is some results with not only using two different point of views, instead of using a lot of point of views. And also using this technique we have created an iPhone application which is called Snappily 3D with collaboration with Humanize. And here are some results using an iPhone. As you can see, the results are quite good instead of being generated using an iPhone. And now it's you can buy it in the App Store.